All right, for the second equation, if sine x equals negative root 2 on 2, well, this value of root 2 on 2 still gives a reference angle of pi on 4. So the reference angle is the same, but the quadrants are now different because sine is producing a negative quantity here. And we know sine is negative in the third and fourth quadrant, so we have new quadrants to deal with. Quadrants 3 and 4. All right, so drawing a picture for that one, it'll look very similar, basically the same picture but turned upside down. Right, something like this. Here, I need reference angles of pi on 4 in the third and fourth quadrants. The reference angle of pi on 4 there, right? That's a reference angle of pi on 4 and a reference angle of pi on 4. Those are not the true angles, of course. So pi on 4 reference, pi on 4 reference. What are the actual angles? Well, if I measure in the positive direction, I will move around here until I get to 5 pi on 4, right? Because this is pi, right? Halfway around is pi. Extra pi on 4 would be 5 pi on 4. So that's what I'm going to call a fundamental solution here of 5 pi on 4 plus any multiple of that times 2 pi. Right, any multiple of 2 pi added to that. And then the same thing for the one in the fourth quadrant. If I move around in the positive direction from here, I will get around to 7 pi on 4 it looks like. So 7 pi on 4, and again plus any multiple of 2 pi. Again, all these are doing is just giving you all those revolutions back to the same position. If I start at 5 pi and 4 and I go around 2 pi, 4 pi, 6 pi, 8 pi, keep going, I'll end up in the same terminal side. So these are all legitimate angles that will cause sine of x to become negative root 2 on 2 specifically. All right, so now we've got 4 expressions here, right? These two and these two that describe our solution set altogether. So there is a better way to write this. And this is all true, but we can condense these a little bit. You can't always, but in this particular problem you can. So if we look at this solution here, right, coupled with this solution here, which I guess is the pi on 4 plus 2k pi and the 5 pi on 4 plus 2k pi. If I look at those two together, then instead of writing this one plus 2k pi and this one plus 2k pi, it would seem that if I had these on the same picture, I would be here. If I go just pi, I would get to this one. And then from here, if I go pi again, I'll get back to this terminal side, and so forth forever. So therefore, these two, right, these two together, I could describe more succinctly as pi on 4 plus k pi, just multiples of pi. If I just go halfway around, right, back to the same position, if I go halfway around, I'll end up at this solution. If I go halfway around from this terminal side, I'll end up back at this terminal side giving another solution again, and so forth forever. So those two you can condense into pi on 4 plus k pi, and then you can play the same game with the latter two. Right, this one here coupled with this one here is the same argument. So this can be condensed down to 3 pi on 4 plus k pi. So that is the true solution set to the whole problem.